Okay, now that we've gone through some of the theoretical sides of things for least squares, we're going to show some examples, and then we'll go to MATLAB and actually do some activities and examples in MATLAB so that we can see how we code these things up. But before we do, I want to take a little bit of time in this next part and talk a little bit about how we can envision, oops, I missed it. How can we envision this idea of a whole bunch of data points and I have some sort of least squares um, residuals. So let me go back to just a few data points. Okay, so here we have 5 data points, and you'll notice then that there's some controls here that I can move around this blue line by defining 2 different spots. And it's likely then that if you can see, the best fit line is probably somewhere close to this. Okay, I can turn on my residuals, and of course those things are the vertical distance away from my line and all the data points. And you'd probably agree that in fact if I chose this as my line, I'm probably not at the best fit line location because I'm underestimating all the data that is found on top of this line. So I've got my residuals and I want to do some sort of way of minimizing these residuals, but in a particular way, by squaring each one of these residuals and then summing them all up. Which means then that if these are my residuals, if I make them into squares, okay, and so now I've got some squares right here, you can see them, okay. There is, of course, one side of the square is going to be the residual, and squaring it is going to be an area such that if I take this square and this one and these two right here, I'm going to sum them all up and they're going to be somewhere around, oh, whatever that is, let's say 85 or so. Which means then that if I go back down to that initial spot, you'll notice then that my sum of squares is much larger. Okay? And right now, this bar to the right shows the summation of all these little squares. So to minimize the area of all those squares is effectively akin to minimizing the sum of the squares of the residuals. And so if I try to guess it, it might be about right here, and then I'm too far, it's going back up somewhere around 96. So that's too far. That looks like it's getting pretty close right there. And if I change this one right here, I can make it a little, that's the wrong way. Whoops. Let's remove those points. I didn't want to add points. I want to click on the square right there, and so I can drop it down a little bit more, and it's still decreasing, and it looks like, oh, I think I about found it right about there. Just by inspection or trial and error, I don't think I can do much better than somewhere around here, like a 75 for the sum of squares of the error. Well, we just figured out the equation for that, and so I'm going to turn on the LS line, and that red line right there is the actual best fit line for a first order polynomial. Okay, I can turn on or I'll turn off my lines, I'll turn on the residuals, and I'll turn on the least squares, and now we can see that this right here is the minimum point. So if I turn on my line, okay, and I turn on my squares, you'll notice then that if I do a pretty close job of getting it close to this red line, okay, I can try all I want. It looks like I'm very close to it right here, but it looks like I have a little bit more to go because that red line has been optimized and it's giving the best fit line. So that's the sum of squares, okay? And now if I add points, my estimate will have to change accordingly. So I'm going to add one more point right here. You'll notice then that there's a bunch of more blue points, and the red is going to be live in the sense that it's going to update always. But you'll notice then that my line is doing much worse. Let me turn off my squares, and I'll just leave on my residuals because I am underestimating a lot of the data. This tells us then that the best fit line, there's one and only one particular line that'll minimize all of the area that are satisfied by those squares. Of course, I can do a good job and bring it back to it, but the residuals will always be there, and there will always be some error unless all these data points are collinear on one particular line. So let me delete them all here. Let me go back to just 2 points. Okay, and if I have 2 points, well, there's of course going to be 2 residuals for my line. You can see them right there, one of the blue lines right here, one of the blue lines right here. But in a least square sense, the residual is going to be 0 because one line can cut through 2 points perfectly, such that there would be a red line right here, indicative of the fact that using least squares regression with 2 points, I can minimize that sum of squares of the error and put it down to 0 with a straight line. If I have 3 points, okay, it's impossible for me to draw a line through 3 points directly. For that, I would have to have a higher order model. So far, I've only been working with first order models, but I'm going to turn on the second order model right here. Okay, and so now you can see that I've got 3 control points. One here, one here, and one here. But the best fit line, which is indicated in red, is still going to do much better than mine using optimization instead of by trial and error. Now, as soon as I add one more point, there's going to be, well, sum of squares. So I can turn on my squares as well, okay, or other squares, and you'll notice that they're not exactly square. That's because the axes themselves, okay, are not isometric, but I can bring it back and make sure that any vertical distance is equal to the horizontal distance there. But essentially, it's the same thing that I want to try to minimize the residual, again, which is the distance between the data point and my model, squared.